All right, welcome and thank you so much for coming here. We are doing the topic, the fundamental counting principle. It is part of the topic probability. In other words, it will be a paper one question and we do probability. And then there is this part, the fundamental counting principle, which is what we are going to concentrate on today. So what is the fundamental counting principle? So in essence, this is a mathematical rule that allows you to find the number of ways that a combination of events can occur. So when you're dealing with the counting principle, you are using mathematics to enable you to find the different number of ways in which a certain event or a combination of events can occur. And so it means when you're dealing with the fundamental counting principle, if there are n ways, n different ways of doing something, and m ways of doing another thing, then it means there are n times m ways to perform both of these actions. So in the fundamental counting principle, we are mostly concerned about the multiplication. If there's n ways of doing something, and then on the flip side, there is m ways of doing another thing, then both actions, both events, there will be n times m ways of performing both events. So we'll run through different ways of dealing with the fundamental counting principle. I want to stress out that there are rules to doing this, different rules for dealing with the fundamental counting principle. And we'll go through each rule. Then we do questions alongside that rule. Each rule, there's about 4 rules. Then from there on, we'll do past exam papers. So let me spend the next couple of minutes doing questions from rule 1. All right, here's rule 1. Rule 1 reads and says, if an operation can be done in m ways and the second operation can be done in n ways, then the total possible number of different ways in which both operations can be done is m times n. It sounds like what I've just said before. Look at this following example. Example number 1. It says, at a movie house, the following movies classified as action and romantic comedies are available. So for action, we have the following movies. We have Terminator 2, that's the first one. We've got Fast and Furious 6, that's the second one. We've got Mission Impossible 3, that's the third one. Taken 4, and the 5th movie is Avengers Infinity War. Then for the romantic movies, we've got The Notebook, that's the first one, Titanic, and The Fault in Our Stars. These are the movies available in a movie house. The question says, how many different movies can be watched from these choices? So we've got one operation in m ways. So look at this way. Action, and then romantic movies like that. Now, it says if one operation can be done in m ways and the second operation can be done in n ways, then the total possible number of different ways in which both operations can be done is m times n. For the action movies, there's 5 choices. So 5 choices of action movies. For the romantic movies, there is 3 choices. So how many different movies can be watched from these choices? Basically, it's just 15 movies. Simple rule as we begin. Put that through. That's example number 1. So maybe you can just write rule 1, example 1. Since I'm recording this, you can always go back and check the question and say, okay, these are my answers. So goes the story. That's example 1. And that's rule 1. But there's more. There's more. So it's just 5 times 3, 5 of the action, 3 of the romantic movies. Let me try another example, still on rule number 1. Example 2 says, how many different ways are there for predicting the results of 5 rugby matches where each match can end in either a win, lose, or a draw? How many different ways can we predict the result of 5 rugby matches where each match can end in either a win, lose, or a draw? So there are going to be 5 matches, and I like using this method. So match number 1, match number 2, match number 3, 4, and 5. Let's see what options we have on match number 1. We could have a win, we could have a lose, we could have a draw. So there are 3 choices in match number 1. Match number 2, still the same amount of choices, win, lose, or draw. Match number 3, same thing. Match number 4, same thing. Match number 5, same thing. And by multiplication, here is the answer. The question, it said, how many different ways are there for predicting the results of 5 rugby matches where each match can end in either a win, lose, or a draw? So 3 times 3 times 3 times 3 times 3, or if you want, 3 to the power 5, which gives you 243 different ways of predicting how these matches will go. That's the first part. Example 1 and 2 on rule number 1. Let's go to rule number 2 and we build up the story. I have a full exercise where I incorporate all the rules and we work it out from there. You let me know when you don't understand something. My key for this topic is to always write down information like this: match 1, match 2. Then these numbers are standing for the choices. So you've got 3 choices of you've got 3 options in match number 1, win, lose, or draw. Same thing in match number 2, stage number 3. So goes the story, and you multiply 243 different ways of predicting the outcome of these events. Rule number 2, let's go. In rule number 2, we hear the following: the number of arrangements of n different things taken in n different ways is n factorial. The number of arrangements of n different things taken in n different ways is n factorial. This factorial part, you have it in your calculator. Just underneath the button mode setup, if you use a Casio, you should be able to see that there is the factorial symbol just underneath that calculator, that button mode setup. Example, let's work it out. Here's example 1, so let's go for it. Consider the word Parktown. You are required to form an 8-letter word, or you're required to form different 8-letter word arrangements using the letters of the word Parktown. The formed words need not to make sense. For an example, here is a word made from the letters from Parktown, and they don't make sense. Doesn't need to make sense, the word of it. But one thing for sure, it must be an 8-letter word. The question then says, how many possible word arrangements can be made if the letters may not be repeated? All right, let's discuss here. I want to make an 8-letter word. 1, 2, 3, 4, 5, 6, 7, 8. My word must contain 8 letters. And then it says, how many possible word arrangements can be made if the letters may not be repeated? So I can't use a letter twice. In other words, if I use P, I can't use him anywhere else in this word. If I use R, I can't use him anywhere else. The letters may not be repeated. So here are my options. On the first letter here, I have 8 options. So I can pick any of these letters. Any, I've got 8. So 8 options here. On the second letter, I can't have 8 options. I can't. I have 7 because already I've used my first choice. In other words, if I pick P here as my first letter, I can't have 8 options again here for P. It's impossible. I must have 7 so that it shows that the letters are not repeated. So then 7 here, and then 6, and then 5. My choices keep diminishing. 4, then 3, then 2, then finally 1. So here's the key for rule number 2. If the particular letters are not repeated, which means your choices keep dwindling. So for the first choice, I used 1 letter and I had 8 choices. Now, because I've used 1 letter for the first choice, I now have 7 choices. I use 1 letter from the 7. Now I've got 6 choices. And now I use 1 letter from the 6, 5, 4, 3, 2, 1. And you multiply all these numbers. 8 times 7 times 6, 5, 4, 3, 2, 1. Mathematically, this is called 8 factorial. So 8 factorial is 8 times 7 times 6 times 5. And then your answer is you have 40,320 different words that you can have if the letters are not repeated. That's example 1. Letters not repeated, rule number 2. Follow my lead. Let me try another one. You may write this down. Example 1, rule 2, example 1. Let's try example 2 of rule 2. Maybe we can get something interesting from there on. I'm about to take this out. Let me take this out. 8 factorial. Here is example 2. Example 2 says, consider the word kingdom. Consider the word kingdom. How many 7-letter word arrangements can be made if the letters 2.1 may not be repeated, 2.2 may be repeated? My word is 7 letters. 1, 2, 3, 4, 5, 6, 7. So my word is 7 letters. And what are my options? The letters may not be repeated for 2.1. That means if I use a letter, I can't use it again. Here are my options, and there are 7 options here. So I'm going to go 7. Once I use 1 letter from the 7 choices, I have 6 choices now. Use 1 letter from the 6. I have 5. I have 4. I have 3. I have 2. I have 1. Get the idea. Your choices are diminishing. So this becomes 7 factorial. 7 times 6 times 5 times 4 times 3. So goes the story. 7 factorial. And your answer is 5,040. That's 2.1. Look at how interesting 2.2 is. In 2.2, we are able to repeat the letters. So if you use a letter once, you can use it again. All right, so I need 7 letters. 1, 2, 3, 4, 5, 6, 7. 7 letters, and let's see what options I have. So what it means in 2.2 is that if you are able to repeat the letters, if you use K, you can use it again and again. So in other words, you can have a word like K, 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 or D, 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 or N, 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 N. You can use a letter all you want, or K, N, K, N, 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 N. So many options that you have. So what happens if I'm repeating the letters? I have 7 choices in position 1. Position 2, my choices don't diminish. I also have 7. I also have 7 because I can repeat as much as I want. My choices are not dwindling. And from that perspective, it's 7 times 7 times 7, 7 times, which is 7, 2, the power of 7, which is 823,453. These are the number of choices that you ultimately have when you repeat that particular or those particular letters. 2.1, 2.2, rule number 2. Let's go to rule number 3. I'll read the rule, then we apply it. It's going to be interesting. You let me know where there's a struggle. Start small, then I'll build up my story from that perspective. All right, let's go further. So it's 8, 2, 3, 5, 4, 3. All right, so it's 5, 4, 3. I think I'm the one that probably made a mistake. Somebody raised their hand, and I want to attend to that person. Let me just find you very quickly. 2 people actually. Go ahead. I'm all ears.
Hello, sir. Can you hear me?
Yes.
I wanted to ask. So for 2.2, do you have to say 7 factorial, or it's only 7 to the power 7 if you can repeat a number or a
If you
letter?
can repeat, it's 7 to the power 7 because your values don't diminish. If you can repeat, so you're always going to have 7 choices at every position. Every letter position, I have 7 choices because I can reuse those particular letters. So it really gets down to 7 to the power 7. Only when you are
So
not allowed to repeat is when you do factorial. Go ahead.
only that.
Yes.
Okay, thank you.
Perfect. All right. There's someone else who has a hand. Would like to attend to that. Okay, I think they've lowered their hand. Let's go to rule 3. Rule 3 says the following. The number of arrangements of m different things taken in n at a time is given by m factorial over m minus n factorial. Okay, that's all good and well. I'm fine with that. Let's show a question so that this rule starts making sense. Example 1. There are 9 different athletes that are hoping to occupy the first 3 places in a 100-meter sprint. 9 different athletes, only 3 places up for grabs. In how many different ways can the first 3 places be occupied? In how many different ways can the first 3 places be occupied? Let's do logic. I have only 3 spaces. I have 9 people. In other words, there's more people than the spaces available. So I only have 9. I have 9 people, but 3 spaces. So not all of them are going to occupy the 3 places. In other words, there's going to be position 1, position 2, and position 3. The other guys will make it to position 4, 5, 6. I can only award the first 3 places. Let's look at my options. For the first place, the second place, and the third place. For the first place, any one of the 9, I've got 9 choices of people. Any one of them can occupy the first place. Once the first place is occupied, I only have an option of 8. 8 different people can occupy second place. Once the second place is occupied, only 7 different people have the ability to occupy the third place. And remember, you can't repeat humans. You can't say someone is in first place and also in second place and also in third place. You can't say 9 times 9 times 9. You can't repeat humans. Once the first position is occupied, those 9 choices, any of the 9 can occupy, any of the 8 can occupy, and any of the 7 can occupy. You multiply. So the number of different ways is 504. You can be confirming my answers. But here's how you do it with this rule that I've put across. Here it was me just basically giving you logic. Here's the idea. So you've got 9 different people. That's 9 factorial over the 9, which is the m minus the 3 positions that you only have. 9 factorial divided by 9 minus 3 factorial, you still get the same answer, 504. So in essence, what it means is that there is only 504 possible ways in which these 9 different people can occupy the first, second, and third positions. You use this rule where you've got more choices than spaces available. I've got 9 choices, but only 3 spaces. So get the idea. Rule number 3, there is more choices than spaces. Let me give an example. Let's say there's a job offer and it's only 3 positions in a company, but 20 people apply. So there's only 3 positions in that company, but 20 people apply. 1, 2, 3 positions in that company, but the CVs that we got are for 20 people. So for the first position in the company, any of the 20 can occupy. Once one person in the 20 is occupied, I only have 19 choices for my second position and then 18 for my third position. Or you could have written it as 20 factorial over 20 minus 3 factorial in respect of rule number 3. So you've got more choices than spaces available. Hence, you use that idea. All right, let me try and show you example 2. Maybe that becomes a bit better on example 2. I'm taking this out so you can have it either this way as an answer or you can have it this way. I prefer this way, but it still gets you to the same point. Okay, I'm ready for example number 2 of rule number 3. Okay. Example 2, something common that we have here in South Africa. There are 12 different singers that are hoping to win the first 3 places in SA Idols. In how many different ways can the first 3 places be occupied? Let's get down to business. What are we saying? What are we doing? How do we play around with this? So the idea is this. Let me read that again so you can understand. Example 2 says there are 12 different singers that are hoping to occupy the first 3 places in SA Idols. In how many different ways can the first 3 places be occupied? All right. So we've got more people than the spaces available. So some of the people will not make it into the first, second, and third position. So I've got 12 people, 12 choices for the first position. I've got 11 choices for the second position. I've got 10 choices of people for the third position. Multiplied right there, ultimately you got 1,320 different ways in which you can award these positions. Or you can say 12 factorial over 12 minus 3 factorial, and it gets you to the same number, 1320. That's what you do when you're dealing with rule number 3. All right, perfect. Let's go do some more. I think I have an exercise coming with many different ways. I'm going to do the exercise with you, but so you may know, maybe someone is still writing. Let me just take it back just a bit. There you are. Let's keep talking and interacting with each other. Check out this exercise here. Okay, I think someone has a hand. You can just lift it up through the platform. There's a part where it says hand, what, but I can find you by your name. All right, I've asked to unmute you. Please go ahead.
Hello, sir. Can you hear me?
Yes, I can.
Since you showed us like 2 ways to do the calculation, in an exam situation, is it like can you use either way, or do you have to use the one with the formula?
You can use either way. Either way would work. Good question. I've showed you 2 ways. Which one can you use? Either of them. Doesn't matter. All right. Thank you. Let's go to the exercises and do a couple of things. Exercise 1. Exercise 1. All right. What I want to do now is I want to ask you guys to try this. I'll give you about 4 minutes or 3 minutes to try this quickly, and then I'll come in and we revise it together. It's basically based on rule 1, 2, and 3, or any of the rules there, as long as it makes sense in the question. Go ahead, 3 minutes. All right. Are you guys not able to see the questions? I think now they're fine. Yeah, we are doing questions, exercise 1. That's what we're doing. Right there. Got about 1.5 minutes. Please finish up. We're good. Let's begin. Exercise 1, question 1. In how many different ways can 8 vacant places be filled by 8 different people? So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 places, there's 8 people. In the first place, I've got 8 choices of humans right there. In the second place, I've got 7, that's 6, that's 5, that's 4, that's 3, that's 2, that's 1. Remember, you cannot repeat humans. And if you multiply every number here in mathematical language, this is as good as saying 8 factorial, which is 40,320 different ways in which 8 people can occupy 8 vacant places. Number 2, in how many ways can 5 vacant places be filled by 15 different people? There's more people, more choices than the places right there. So I can put any of the 15 in first place. I can put 14. Remember, you can't repeat humans. 13, then that's 12, and then that's 11. 1, 2, 3, 4, 5. Multiply them together. You should get an answer for 360,000, 360,000. 360,360. Then the other way of doing question number 2, which is what one of you was asking, 15 factorial, rule number 3, over 15 minus 5 factorial, which is basically 360, 360. That is question number 2. Number 3, find the number of ways that a judge can award first, second, and third place to a competition with 10 contestants. 10, 9, 8. There is 720 ways of doing this. Or it will be 10 factorial over 10 minus 3 factorial, all this giving you 720 different ways in which that can be done. Just so I can reiterate, question number 1, in how many ways can 8 vacant places, so there's 8 places, 1, 2, 3, 4, 5, 6, 7, 8 places. How many people are available? 8. So for the first place, any of the 8 can enter. Once I've used one choice out of the 8, for the second place, I have 7 choices of humans. Once I've used 1 out of the 7, I have 6. Your numbers keep diminishing because you can't repeat humans. If the first person occupies the first vacant place, he can't occupy or she can't occupy the second place as well. Can only occupy one space at a time. So your choices keep diminishing. All right. I'm hoping that people got this right. If there's any question, let me know. Let me build up my story. I have more questions. Let me take this out. Gone, going. Gone. I've got question number 4 as well. And I'm continuing with exercise 1. Consider the word oranges. I'm going to do this one with you. Consider the word oranges. Let me find out how many letters this word has. It's got 1, 2, 3, 4, 5, 6, 7. 7 letters. Perfect. How many 4.1? How many 7-letter word arrangements can be made if the letters may be repeated? 1, 2, 3, 4, 5, 6, 7. All right, help me. How many choices do I have here for the first word? I need the letters may be repeated. 7 choices, right? Any of the 7 letters would work. 7 even as well here. I see your numbers. Thank you. Appreciate. 7 as well. 7 as well. 7, 7, 7. And it means 7 to the power of 7, or 7 times 7 times 7 times 7, 7 times 823,543. That's 4.1. As I go ahead, let me know, stop me where you don't understand. That's 4.1. Let's try 4.2. How many 7-letter word arrangements can be made if the letters may not be repeated? 1, 2, 3, 4, 5, 6, 7. We're not repeating the letters now. So which means we use one letter, can't use it again. So that means 7, 6, 5, 4, 3, 2, and then 1. So then this becomes 7 factorial, which gives me an answer of 5,040. So that's 4.2. Let me know again if there's a struggle. 4.3. 4.3. In question 4.3, we want a 4-letter word. That's question 4.3. We just want a 4-letter word. Okay, so let's see what's happening with the 4-letter word there. Checking this out. How many 4-letter word arrangements can be made if the letters may not be repeated? 1, 2, 3, 4. So I have 7 choices of letters, but my word is 4 letters. And the words or the letters may be repeated. So if I use a letter once, I can use it again. So I have 7 choices. Even here, I've got 7 choices because I can use it again. I've got 7 choices. I've got 7 choices. That's 7 to the power of 4, which gives me the answer of 2,401. That's what I have, 2,401. But there's more. Work with me from that perspective. How many 4-letter word arrangements can be made if the letters may not be repeated? So the letters may not be repeated. So still 4-letter word, but this time the letters are not repeated. Maybe someone is still writing. Let me bring it up. Let me just write this down here. 1, 2, 3, 4. What's your answer? I'm here. What's your answer? I'm on 4.4. What's your answer? Somebody says 840. 840. Just want to confirm if we're dealing with 840. Oh, lovely. 840. Why? Because if I use a letter here, can't use it again, can't use it again, can't use it again. So it's 7 times 6 times 5 times 4. If you want, it's 7 factorial, rule number 3. 7 minus 4 factorial is equal to 840 different ways of doing this. Appreciate. We're good to go. Let me know where there's a struggle. I want more, right? Somebody says, say, can you please rephrase 4.3? How many 4-letter word arrangements, I'm reading, can be made if the letters may be repeated? Okay. Your answer is the one that I'm just going to put a boundary on, this one. So you're having a word with 4 letters, 1, 2, 3, 4. And you're choosing the letters from 7 choices, the letters of the word oranges, arranged in whatever way you want. So in position 1, any of the 7 letters here can work, any of them. In position 2, because I can repeat, I can use the same letter, so my choices don't diminish. My choices don't diminish. My choices do not diminish. Always multiply. Always multiply. All right, perfect. I'm hoping that you get that. I want to move on to my next one. I'm going to skip question 5 because it's generally the same idea like question 4, but I want question 6. Yeah, this one is mine. So work with me on question number 6. I'm just going to skip 5. When you watch the video again, you can always do 5 all by yourself. I want 6. Here's the story. Let's go. The digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are used to make a 4-digit code. Okay. Here's the idea. So I'm going to make a 4-digit code. And from that 4-digit code, I use the digits 1 to 8. Let me go back again. The digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are used to make a 4-digit code. So my code 1, 2, 3, 4. My code must have 4 digits. And I can use, or these are my choices. So when you say 0 to 9, that's having 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's 10 choices that you have there. So digits 0 to 9 are used to make a 4-digit code. Then it says to me, how many different codes are possible if the digits may be repeated? So let me see my choices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 choices of the digits. How many different codes are available if the digits may be repeated? So in the first position, any of the 10 digits can work. In the second one, any of the 10 can work. Any of the 10 can work. Any of the 10 can work. So I'm looking at a situation of 10 to the power of 4 right there, or 10 times 10 times 10 times 10 right there. And the answer should be 10,000 different ways. There you go, 10,000. All right, that's 6.1. You let me know where there's a struggle. 6.2 says, how many different codes are possible if the digits may not be repeated? So once you use a digit, you can't use it again. Use it once, you can't use it again. All right, let's work it out. So it looks like if I use a digit, I can't do it again. I can't use it again. For the first position, I've got 10. For the second position, I have 9. Then I have 8. Then I have 7. So it's 10 times 9 times 8 times 7, which should be, I think from what I'm seeing here, 5,040, if I'm not mistaken, times 8 times 7. Yes. So when you multiply 6.2, it's 5,040 different codes that you may have. All right. Somebody says, why didn't we say 9 to the power of 4? I'm confused there. 9. Which 9? Because I have 10 choices, including the 0. I haven't read them. 1, 2, I haven't counted them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Count the 0 as well. And it is part of your choices. So it's not 9 to the power 4, it's 10 to the power 4. You got 10 choices. All right, I'm hoping that you understand that. 6.2, we're done. Let's try 6.3, where it gets interesting. All right, 6.3. How many codes are greater than or equal to 4,000 and are exactly divisible by 2? The digits may be repeated. My code must have four digits, my code. The question says, how many codes are numbers that are greater than or equal to 4,000 and are exactly divisible by 2? Work with me. So my code must be 4,000 or greater. My code. Not just that, but it must be divisible by 2. So that means I must be sensitive to the starting numbers. My code must be 4,000 or greater. In other words, for the first position, I can't allow the digit 0 to occur, because it becomes 0 something, which is a number. that is not greater than or equal to 4,000. I can't allow 1, because once I have 1 as part of my choices here, it'll be 1,000 and something. I can't allow 2, 2,000 and something. I can't allow 3, 3,000 and something. My choices for the first position are 4, the digit, 5, 6, 7, 8, and 9. Any of these could be applicable in the first position, which means in essence, all I have is 1, 2, 3, 4, 5, 6. I have 6 choices of numbers in the first position of my chord. I can't put 1, can't put 2, can't put 3, can't put 0. Because once I put that, then my digit starts with 1,000 and something. 2,000. I don't want that. I want numbers that are greater than or equal to 4,000. All right, work with me from that. Work with me from that. Then look at the next one. There must be divisible by 2. There must be divisible by 2. Divisible by 2 means that the last digit must be either 0 or an even number. Because every time you've got a chord where you can divide by 2, the last number of that chord, the last number of the chord must be 0, 2, 4, 6, or 8. Choices 0, 2, 4, 6, or 8. 1, 2, 3, 4, 5 choices. You've got 5. So the first and last position are very sensitive because I need to be able to get to a point where the chord is greater than or equal to 4,000 and divisible by 2. And they said the digits may be repeated. So which means for this second position, I've got 10 choices. Any of the 10 can work. For this third one, I also have 10 choices. The choices are limited on the first position because I want to ensure that my chord is greater than or equal to 4,000. And then on the last position, because I want to ensure that it's divisible by 2. And so in essence, it's just 6 times 10 times 10 times 5, which gives you 3,000 choices. And that's your answer right there. Perfect. All right, you let me know where there's a struggle. 3,000 choices. And that's just what it is. Try 6.4. I'll give you 1 minute. Try 6.4. Someone raise their hand before I do 6.4. Go ahead. I'm listening. I've unmuted you. You should be able to speak. Okay, I'm not winning with this. Let me try another one. Go ahead.
Sir, I was saying, is there a formula for that, or must we just know how to do it?
There's no formula, it's logic. You need to be able to read it and then say, okay, what choices do I have? How far do they go? And so goes the story. Let me repeat. I see people asking me to redo this. Let me do it. Okay, gone. 6.3. How many chords are numbers that are greater than or equal to 4,000 and are exactly divisible by 2? Okay. Okay, the screen keeps going blank. Not so sure why. Don't like this. But let me go back. How many chords are numbers that are greater than or equal to 4,000 and exactly divisible by 2? All right, 6.3. 1, 2, 3, 4. Remember, your chord must have 4 numbers. Just 4. Okay, sharp. For the first position here, my code can't start with 0. Because once it starts with 0, it means any other numbers that follow will not be greater than or equal to 4,000. Neither can you start with 1 because my code will read 1,000 and something. Please don't make a mistake. Choices, right there. It can't start with 2 because it becomes 2,000 and something. It can only start with 4 or 5 or 6 or 7 or 8 or 9. That's as far as it can go. So 1, 2, 3, 4, 5, 6. 6 choices of numbers. This is not a chord. It's just 6 choices. Please don't make a mistake. This is 6 choices. I only can get 6 choices for the first position. I can start my number, my code with 4, 4,000 and something, 5, 5,000 and something, 6. Whatever I can do, it's actually greater than or equal to 4,000. Then it must be divisible by 2. Divisible by 2 meaning the last position must be sensitive. Any code that you can divide by 2 ensures that your last number is 0 or 2 or 4 or 6 or 8. I'm taking from my choices. So the number of choices for the last position is 5. 0, 2, 4, 6, 8. It's 5 choices. Then there's still more to put here to make a proper code. The choices for the second position is 10. Any of the numbers can work, right? Because they said the digits may be repeated. Any of the numbers can work here. Then also for this one, it will be 10. Any of the numbers can work. You see, if they had said the digits may not be repeated, I was going to say 6, then 5, right? If they said it now, look at me show how interesting it is. So I've used one number here. I've used another number there. So I've used one number there, one number there. Perfect. So I've used 2 numbers. One number at position 1 and the other number at position last. So they say the digits may not be repeated. Let's say they say that here. So it means right here, I can't put 10 choices because I've already used 2 numbers here. So here I can put 8 choices because I've used 2. I needed the number of choices that I had is 10. Out of the 10, I've occupied position 1 and position last. I'm left with 2 positions and 8 choices. So for the second position, for this position here, I can only put 8. Then for this one, I can only put 7. That's if they say the digits may not be repeated. If they say the digits may not be repeated, that's what it means in essence. So you can't have them coming over and over again. So you have used 1 digit there, you've used another digit there, you've used 2 digits out of 10. So now you've got 8 choices for this position. You used that one from the 8, then you got 7 choices for that if they say the digits may not be repeated. But in our question, they may be repeated. And so when you multiply, your answer is 3,000 different chords that can be made. 3,000 different chords that can be made. All right, 6.4. Let's go to them and let's see how far we can go. Let me know where there's a struggle. We're having a bit of some fun. It's a beautiful topic, the counting principle. I'm taking this out. Going. Remember, your answer is the first one. This one was just me saying if the digits may not be repeated. There's questions I'm going to do that have similar connotations. Don't worry. Out, gone. Somebody has a hand. Go ahead.
Hi, sir.
Hi.
I have a question.
Yes.
Why did we include 0 on the last digit?
Okay. So your question is,
Because
go ahead. You're saying?
if I think they're saying that it should be divisible by 2, so we should include even numbers. Am I correct?
Yeah, and 0.
But
And 0. Because if it's divisible by 2, any number with 0 at the end, you can divide by 2. Your first chord is actually 4,000. Your second chord is 4,002. Your third chord is 4,004. So the first chord, is it greater than or equal to 4,000? Yes. Can it be divided by 2? Yes. So any number that ends with 0 or 2 or 4 or 6 or 8 can be divided by 2. Are we good on that?
Thank you, sir.
Perfect. Lovely. Thank you so much for asking that. All right, let's go further. There's more that's coming as we go on along. 6.4 has this idea. 6.4 says, how many chords and numbers that are equal to 4,000 and exactly divisible by 2? This question will be 1 mark. This is a part exam paper, by the way. Part exam paper question, by the way. What's your answer for 6.4? It's 1 mark. How many chords and numbers that are equal to and are exactly divisible by 2? Some are saying 1. Someone is saying 2099. 1, 2099. The answer is 2099. Let me explain. Okay, I know, right? Welcome to school. 500. Yeah, check this out. In 6.3 and 6.4, look at the difference between these two questions. In 6.3, how many chords are greater than or equal to 4,000? Greater than or equal to 4,000. In 6.4, how many chords are equal to, are numbers that are equal to 4,000? How many chords are numbers that are equal to 4,000 and exactly divisible by 2? I don't like how this thing is worded here. Let me word it differently so that maybe that's where the problem is. Now I understand where you guys are coming with the 1 here. I actually have this worded in a different way so that at least you guys can get to understand. So I would have said how many chords and numbers that are, then I'll take this word out, greater than 4,000 and exactly divisible by 2. All right, so maybe that's where the question, so you were right to say the 1 when you read it like that. So let me just change it because I really want it to look a bit different. How many chords and numbers that are greater than 4,000 and are exactly divisible by 2? Okay, let's get down to business. From 6.3, we had 3,000 chords that are greater than or equal to 4,000. So for 6.3, the first chord was 4,000, and like I had said previously, 4,002. But this time, and we did 3,000 different chords. So this time, they're saying to ourselves, no, 4,000 is gone. We want chords that are greater than 4,000. So we have taken chord 4,000 out. We just take 1 chord out. So what's remaining is 2,099. Those are the number of chords that are greater than 4,000 and exactly divisible by 2. So you just go back and relate that to 6.3 and you'll be able to get that done. So I just changed the question there, greater than 4,000 and exactly divisible by 2. All right, let me go do more. I want something to do with arrangements of objects. Yeah, arrangements of objects in a row. Let me have that for the next one. Yes, this one here. All right. Maybe write this as a subtopic. Arrangements of objects in a row. This is a very interesting question. I saw questions like this when I was just going through this. I just saw questions that have to do with all that. Okay, are people asking me to repeat? Oh, okay, I can. Yeah, I can. I can go back. Sorry about that. Didn't notice. Are you asking me to go back to which question? Which question do you want me to go back to? .4. Okay, sharp. So I need to cancel this. Okay, let me do this. So it becomes easier for everyone. Right, 6.4. How many chords are numbers that are greater than 4,000 and are exactly divisible by 2? In the previous question, we found 3,000 different chords that are numbers that are greater than or equal to 4,000. That was 6.3. 6.4 says, how many chords are numbers that are greater than 4,000 and exactly divisible by 2? In the previous one, it was greater than or equal to 4,000. That was the previous one. Greater than or equal to 4,000. So in this case, for 6.3, your first chord was 4,000. Your next chord is 4,002, 4,004, until you've got 3,000 different chords. Okay, sharp. But then in the next one says, how many chords are numbers that are greater than 4,000? So I can't use the chord 4,000 because I'm looking for chords greater than 4,000. So the choice of the chord 4,000 is gone. I can't have that. So my first chord now starts at 4,002. So earlier on, I had 3,000 chords inclusive of 4,000. But I want something greater than 4,000, not greater than or equal to. So instead of 3,000 chords, I eliminate one chord, and I've got 2,999. And that's how your answer looks like. I'm hoping it's better. Okay? I'm hoping. All right, let's go further. I wanted the objects in a row from there on. Are we okay now? Are we good? All right. There's your Bible. What you talk about? It's called school. All right. Understood. Thank you. Appreciate. Now look at this dynamic question. This is just objects and their arrangements in a row. So work with me from there. Follow me. A family photograph needs to be taken. Okay, hold on. Let me work it out. Somebody says, nah, we're not good. Okay, maybe a similar question. Let's leave it and do a similar question. Because that's just the best way I've explained it, right? You've got 3,000 chords. The next time you can't include 4,000 as a chord. So you had 3,000 chords, which included 4,000. It was, the 6.3 was greater than or equal to. That was 6.3, and it's greater than or equal to. Take one chord out. Which one? 4,000. Why? Because 6.4 does not require 4,000. I want things that are greater than 4,000. 4,000, the chord is gone. It's gone. How many chords did I have when 4,000 was available? I had 3,000 chords. 3,000 different chords. Now that 4,000 is gone, I've got 2,999. Azo. Come on, man. Come on, guys. You guys can get this right. Let me move on. I want another thing. I'll come back to this via other questions. Okay? A family photograph needs to be taken for a family of 5, inclusive of mother and father and their 3 children. There are 3 males and 2 females in the family, and all of them need to sit in one row for the photograph. Now, this is classical maths. Follow me. Follow my idea. Work with me. I'm going to read again, and you guys can work it out. A family photograph needs to be taken for a family of 5, inclusive of a mother and father and their 3 children. There are 3 males and 2 females in the family, and all of them need to sit in a row or in one row for the photograph. In how many ways can 3 males and 2 females sit in a row? 5 people in total. 1, 2, 3, 4, 5. In how many ways can 3 males and 2 females sit in a row? So for the first position, we can have any of the 5. So it's going to be 5. Any choice, 5 of them, any of the 5 can occupy the first position. 4, 3, 2, and 1. So it's just 5 factorial. Any of them can occupy that part. So it's 5 factorial, which is basically 120 ways in which this family can sit in that row. There's more. Let's go. So that's just A. Look at B. Let's do B together. B says, in how many ways can they sit in a row if the father and the mother must sit together? The father and the mother must sit together. Now, this must never change. The father and the mother must sit together. Listen to how physics or maths actually starts looking. Somebody says repeat. Okay. All right, no problem. There's 5 people and 5 spaces. Ne? Just 5 people, 5 spaces. Okay. I'm going to do another lesson on this topic, but I'm going to be doing questions only, high-end questions. So, but that one's going to be paid for. So you need to attend it if you still don't understand. 1, 2, 3, 4, 5. Perfect. There's 5 people. How many people can occupy the first position? Any of the 5. 5 choices. Mom, dad, any of the 3 children. And for the next one here, 4, 3, 2, 1. Remember, once one person occupies this chair, I can't have the same person occupying the second chair as well. That's why now, let's say the dad is occupied here, the father. That means now there's 4 choices, which is the 3 children or the mother for the second position. Let's say one of the children sits here. Now there's only 3 choices, 2 children and the mother. You see, it keeps diminishing over and over again. All right. So that's 5 times 4 times 3 times 2 times 1, which is 5 factorial. The next one says, in how many ways can they sit in a row if the father and the mother must sit together? 1, 2, 3, 4, 5. Now. Let's do some maths. I love this. The father and the mother must sit together. We don't care how the children do things. We don't care whether the first born, second born, or third born, whatever. We don't care. Father and mother must sit together. So we bungle this. That's what I usually tell my students. Bungle it. This is not changing. Father, mother must sit together. So you count and say 1. Then you say 2. Then you say 3. Then you say 4. So that becomes 4 factorial. Multiplied, but check this out. I can have the father, mother, or mother, father. All right? Mother, father, or father, mother. So in other words, I've got 2 options. I can start with the father, then go to the mother, or with the mother, then go to the father. So I've got 2 options right here, FM or MF. And so it's 2 times 4 factorial. Let's go back. The father-mother situation must never change. Bungle it. Bungle. That's all I say. Bungle it. Count 1. Count 2. Count 3. Count 4. Oh, let's do some maths. Let's do some maths. Follow my lead. One more time. Let's break it down. I'm taking this. I'm starting it from scratch. Let's go. It says, in how many ways can they sit in a row if the father and the mother must sit together? Got 5 people here. 5. 1, 2, 3, 4, 5. And we're told that the father and the mother must sit together. So this must never change. While they take the photo, the father and the mother must sit together. So you bundle that and start counting. Start counting. 1, all right. 2, okay. 3, okay, 4. So that's 4 factorial. 4 factorial. But your choices are, you can have father starting, then mother next, or mother starting, then father next. So then this 2 is a combination of FM or MF. And so at the end of the day, you got 48 ways in which this can be arranged. That's B. Bungle it. What doesn't change? Bungle it right there. 48 different ways. Follow my lead. Follow my lead. All right, I'm ready for my next one. That's B. Let's try C. Work with me, fam. Work with me. So now we're becoming more specific. Look at C. In how many ways can they sit in a row if the males and the females are to sit together? So in other words, I'll have the males on their on, then the females on their on. Let's go. 1, 2, 3, 4, 5. So what must not change? Males on their on. What else? Females on their on. Bungle it. Males must sit on their on. Females must sit on their on. Bungle it. Count. 1, then 2. So I've got 2 factorial right there. Then I have options. Look at this. Male 1, male 2, male 3. So I can start with male 1, male 2, or male 3. Or male 2, male 1, and then male 3. Or male 3, male 2. So you got 3 options. In any of them can work it out in any of the positions here, right? Male 1, male 2, male 3. That gives me 3 factorials. These are for the males 1, male 2, and male 3. Even here, I continue with the multiplication. Female 1, female 2. I can have female 2, female 1, or female 1 and female 2. That's again 2 factorial. That's the female 1, female 2 situation. Write this down like this. This 2 factorial is the bungling. Males on their on, females. In other words, I can start off by having all 3 males first, and lastly, all 2 females. Or all 2 females first, and lastly, all 3 males. That's the 2 factorial. Amongst the males, I can have male 1, male 2, male 3, male 2, male 1, male 3, whichever you want. Amongst the females, female 1, female 2, female 3, female 4. Female 1, female 2, not female 3, female 4, just female 1, female 2. I'm reading your numbers here. I got a bit distracted. So then at the end of the day, 3 factorial times 2 factorial times that's 24 ways. All right. Arrangements of objects in a row. Maths. Let's go. All right. I'm ready for the next one. You let me know where there's a struggle. That's B. No, that was C. This is C, what I was doing. Let me go to D. D. All right, here's D. Here's D. D says, in how many ways can they sit in a row if just the females are to sit together? If just the females are to sit together. So just the females on their on. I really don't care how the males do their story. Just the females are to sit together. Bungle. Bungle. Females. Bungle. Let's go. 1, 2, 3, 4. That's 4 factorial. Then for the females, female 1, female 2, female 2, female 1. That's 2. Didn't even say 2 factorial, still fine. And so therefore, at the end of the day, this becomes 48 ways. That's for D, 48 different ways. That's for D. All right. I'm ready for the next one. I love your participation is beautiful. Beautiful to watch. So again, fam, bungle. That's it. My Betty, females, bungle. The females are to sit together, bungle. Start counting, bungle. 1, 2, 3, 4 factorial. Then 2 coming from the fact that female 1, female 2. And then the males can do what they want. We really don't care much about them. We just want the females next to each other. Try E. Try E. Let's see. 1 minute. Try E. I'm ready. Let me hear your answers. 36, 18, 6 squared. Let's see. Let's go. In how many ways can they sit in a row if just the males are to sit together? 1, 2, 3, 4, 5. Males alone, please. 1, 2, 3. There are 3 males. So bungle them. Thank you. So I go 1, 2, 3. That's 3 factorial. For the males part, male 1, male 2, male 3, male 2, male 1, but blah, blah, blah. That's 3 factorial as well. So at the end of the day, the answer is 36 different ways of doing this. Very important that you get this, 36 different ways of dealing with this. All right, it's good. We're great. F, try F. Ooh, I want to see this happening. Try F. Try F. So that's E, and I want you guys to try F, and let's see how far it goes. Let me know again where you don't understand. But for me, the bungling is important. Once they say these ones must sit together, bangle, 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 then count and then work it out from there. Okay. Let's try F. 1 minute. Somebody says, say, shouldn't it be 3 factorial times 2 factorial? Why? Maybe you can explain that to me. Because from what I'm seeing here, hold on, let me just do this. Okay. From what I'm seeing here, I only have 3 males, and I bungle them and I count 1, 2, 3. That's the 3 factorial. Then the 3 factorial again here is for the male 1, male 2, male 3, or male 2, male 1, male 3. Let me hear that. All right. F, here we go. In how many ways can they sit in a row? If the males and the females are to alternate. Oh, love this. Males and females are to alternate. Yo, let's see how it goes. So the males and the females are to alternate. Let's see how it goes. Let's work it out from there. 1, 2, 3, 4, 5. I'll show you something that doesn't work here. Then, so males and females are to alternate. It means male, female, male, female, male, female. So there must be one next to another. So I can have it as male, female, male, female, and male. Remember, there are 3 males and 2 females. So this must always remain the same. Male, female, male, female. Then unfortunately, one of the males will just be alone. Here's the idea. I can't start it like this. Let me show you what doesn't work. I can't start with a female, because that means I need to put a male, then a female, then a male, then a male. This is not what they want. They don't want males next to each other. So they want male, female, male, female. They alternate. So in whatever you do, if you want to alternate properly, you can't start at the first position with the female. You have to start with the male. So then here's what must never change. 1, 2, and then 3. So that's 3 factorial. Now, check this out. I can't have male 1, female 1, female 1, male 1. I can't. This must never change. But here's what I can do. Check this out. I can start with male 1, female 1 combination. Then the next combination is male 2, female 2 combination. Right? So I've got 2 choices here, 2 factorial, which is basically the male 1, female 1 combination. I can start with that. And then the male 2, female 2 combination, I can go ahead with that. So that's how the 2 factorial comes into life. All right? That's how it comes into life. Male 1, female 1, male 2, female 2. Multiplied by here, which is 1. This male must never change. It's always going to be one choice, and that choice is a male And when you multiply them, you got 12 ways of doing this. Welcome to mathematics. I've got more crazy ones coming up. Talk to me, fam. Someone raise their hand. Mina, I unmute. Go ahead. I'm listening.
Hi, sir. How are you?
Great. You?
I'm good. I wanted to ask if I answered this way. I said in the first position, any of the three males can occupy the space, and then second one, any of the two males can occupy the space. Females, I mean, and then third one, any of the remaining two males can occupy the space, and then fourth one, the remaining female occupy the space, and then the last one, the male occupy the space, and then I multiply them and they give me 12. Is it wrong?
Perfect. It's okay. It's a good way of thinking about it as well. I would take that.
Okay, thank you, sir.
Thank you. You did well. All right. Let's go. I'm ready for my next one. So that's arrangements of objects in a row. Interesting mathematics. Now let's go further. Got more people, right? Somebody says, say, would it be wrong if I say it's 3, 2, 2, 1, 1? Okay, which is what she's saying, right? I think this is what she was saying. It's still fine. It's still fine. I'm still okay with that. Then somebody says, say, please explain it one more time. Okay, no problem. Don't worry, guys. I need you to get this right. You need to trust yourself when you're doing these questions. It's quite logical. For me, this topic is very interesting because it's how you make, for an example, lotto numbers and why you'll never win the lotto. It's the counting principle. Too many options available. Too many numbers available. Too many on any position. Why you can't win much when you bet? Because there's just too many infinite number of options. How you make ID numbers, how you make passwords, how you make number plates, right? So you want to use numbers, even letters, to enable you to get as much of a choice as humanly possible. Sharp. Here we go. Somebody says, please repeat. Alternate, male, female, alternate. 1, 2, 3, 4, 5. Let's go. I want a male here. Next up, female. Want a male here. Next up, female. Want a male here. This must never change. Male, female next to each other. Bungle and count. 3 factorial. Thank you. Where's the 2 factorial coming from? I can have the first male-female combination starting, and then the second male-female combination coming through. Or I start with the second one and like that. So in other words, I can have male 1, female 1 starting, male 2, female 2, or I can have male 2, female 2 starting, then male 1, female 1 coming through. Then the other guy who's carrying the candle is on his own. That's 12 ways. It's like going out with your friends and you're single. You're always going to be the one seated here, taking pictures. We're happy. We're happy. Sit down. Oh, right. Let's go. I'm ready for my next one. Right there. So I'm hoping that people can understand, can get this right. And we take it up from there, so that we can have as much fun as is possible. Perfect. Gone. Rule number 4. All right, so rule number 4, I'm going to use questions to actually show it, just like what I did with the other one. This is the last rule that I have here. And then from there on, I will then take it up with other questions and see if we can do some past exam papers, time permitting. Like I said, I am going to do, this for me is just the introduction, just the hi, how are you of this topic. And then I am going to do another part 2 of this, the counting principle, so that we are thorough and we know everything. Rule number 4. The number of different ways that n letters can be arranged where m1 of the letters are identical M2 of the letters are identical, M3 of the letters are identical, up to Mn of the letters are identical, is given by that where the repeated letters are treated as identical. Okay, I know. What is this that you just read say? I know. I got your back, Ndwana. Let me show you how it works. Example 1, rule 4. Write it down. Rule 4. Example 1. Consider the word winning. Winning. One thing about this word is that it has repeated letters. There's 2 I's and 3 N's. 2 I's, right, and 3 N's. That's basically what you have. Consider the word winning. How many word arrangements, 1.1, can be made with this word if the repeated letters are treated as different letters? So there's 7 letters here. 1, 2, 3, 4, 5, 6, 7. There's 7 letters. How many word arrangements can be made if we treat each letter as a repeated, each repeated letter is different? In other words, here on this position here, I can use any of the 7. I know they're repeated letters, but we treat them as different for 1.1. 7 choices. I use 1 letter, can't use it again. 6 choices, then 5 choices, then 4, then 3, then 2, then 1. Notice that in this question, I probably forgot to put it, you're not repeating the letters. In other words, you can't use a letter twice. You can't have N, or blah, 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 blah. So it's use it once, and that's basically it. So let me go back again. How many word arrangements? We did this in our first couple of questions. How many word arrangements can be made with this word if the repeated letters are treated as different letters? Okay, so you've got this 7 options here. Any of these letters, even though they're repeated, we treat them as if they're different. 6, 5, 4, 7 factorial. Your answer is 5,040. 1.1. Okay. 1.2, I love your participation. You guys are wonderful. I'm enjoying this lesson with you. 1.2, let's go. How many word arrangements can be made with this word if the repeated letters are treated as identical? Rule number 4 respects the fact that they are identical letters. So here's the idea. The identical letters are I, and then the N's. There are 3 of them. 1, 2, 3. So then how many words can I get if the repeated letters are treated as identical? So here's what you do, the rule number 4. It says 7 factorial, which is basically all your options that you have, divided by the repeats. There's 2 repeats for UI, so the first I, the second I, that's 2 factorial, times 3 repeats for UN, the first N, the second N, the third N. You can place them in either way, first N, second N, third N, or whatever the case could be. So this becomes 7 factorial over 2 factorial times 3 factorial. You divide by the repeats, rule number 4. So in essence, your answer is 420 ways. So remember, you're saying 7 factorial is when you treat them as if they're different. But then with rule number 4, you are ensuring that you respect that the repeated letters are identical. So divide your first options, 7 factorial, by the divide or by the repeated letters. So the 2 factorial is for the I, the 3 factorial is for the N's. Remember, there are 2 I's here. Let me just write them as I's like this. Then there are 3 N's. So you do it like that when it comes to repeated letters. Okay. So someone says, say, may you please give us the general formula for rule 4? I find this very difficult. Thank you for the question, though. I find it very difficult to actually answer that kind of question because what it simply means is take your options, 7 factorial, divide by the repeats, however many they are. So I've got only 2 repeats for n and for I. 2 factorial for 2 i's, 3 factorial for 3 n's. Imagine if there was more letters that are repeated. I'll needed to add them as a denominator as well. So basically, you just, as you treat them as identical, you eliminate them from your choices. That's why you divide. Maybe that would be the best way to put it across. As you treat them as identical, you eliminate them from your choices. That would be the best choice. All right, let's look at 1.3. How many word arrangements can be made with this word if the word starts and ends with the same letter? 1, 2, 3, 4, 5, 6, 7. Okay, so it can start with I and end with I. Or 1, 2, 3, 4, 5, 6, 7. It can start with N and end with N. Okay, those are my options. So this must never change. And it must start with the same letter everywhere. Right? Start and end, same letter. So let me look at the first option here. What happens here? If it starts with the first letter, I, and the last letter I, inside here, you've got only 5 choices of letters here. So that's 5 factorial right there over right here. So think about it this way. You've used one letter here, I, and used another letter there, I. So you've got only 5 letters that you can play around with here. And then divide that by the repeats that are available here, which is just 3 repeats of the letter N, right? N, right there. So let me do this. So it's 5 factorial over 3 factorial for this I business, because the 3 factorial respects that I have 3 repeats about N inside here. Then on the flip side here, I've already used 2 letters which are the same, which is N and N. So again, it's 5 factorial over the repeats inside here. It's 2 factorial. The repeats are I. So there's 3 N's, remember, but now that I've used 2 of them, I can't consider it as a repeat inside here between the letters, between the spaces that are 5 spaces. So I can't use it as another repeat because already there's just 1 N remaining because I've used the other 2. So here the 2 factorial will just respect what I and I belong to. One more time. This is gone. Let's go. I'm reading the question 1.3. How many word arrangements can be made with this word if the word starts and ends with the same letter? 1, 2, 3, 4, 5, 6, 7. Okay, you can start with I and end with I. Sharp. 1, 2, 3, 4, 5, 6, 7. You can start with N and end with N. Sharp. Let's start with I first. Occupied, occupied. So you got 5 options to play around with. Over the repeats between the 5 options are 3 of them, which is the N repeats. Then for this one, I've used 1 letter already. Use 1 letter, that must not change. And in between here, I have 5 choices again. So the 5 choices over the repeats here, which is 2 factorial, the repeats for I. Then I add them together and I get 80 different ways. And that's your answer for 1.3. Starts and ends with the same letter. And that's how you do it. So you break it down from that perspective. All right, I'm ready. I'm ready for my next one. Work with me. Work with me. Let me see something here. Okay, somebody says, where is the 5 from? I didn't get the part. Or so we use the repeated letters. We can't take W. Maybe I'm not understanding what's going on. Maybe you can just raise your hand and I help you out. Guys, this topic is crazy. It's not difficult. It's interesting. It's a bit tricky here and there, but it's something that's doable. All right, let me, I see your hand. Let me work with you. Yeah.
Sir, I was asking that we only use the repeated letters. You can't take W, for instance.
No, we can't, because they've told us what should happen in 1.3. I can only work with I and I. W is not repeated, by the way. I can only work with N
Yes.
and N. Yeah, so I can only take those guys. And our W are found here in the 5 choices here. And so you can find
Okay.
Yeah, so you can't. But in line with what you just asked, look at 1.4, which I'm going to do. Maybe you'll see it when I do 1.4. Ne?
Okay, sir. Thank you.
All right. I'm ready. 1.4. In how many word arrangements can be made with this word if the word starts with W and ends with G? That must never change. I'll start with W and end with G. 1, 2, 3, 4, 5, 6, 7. All right, so I've used W already. I've used G already. So I only have 5 choices here. So it's 5 choices. And then the repeats. So I'll have the I repeats, which is 2 of them. I'll have the N repeats, which is the 3 of them. Then from there on, my answer is 10. Just 10 different ways. That's 1.4. W and G. Thank you. Appreciate. Let's go to 1.5. 1.5. Quite interesting. 1.5. Yeah, let me just take this part off. So I don't have to be writing this. 1.5. 1.5 says how many word arrangements can be made if the word starts with the letter I. So I, that's definitely the start of the word. So now you have 6 options because this one is already occupied. And then you must respect the repeats. So if I use I, there's only one I amongst the 6. It's not repeated. The N's are repeated, however. So that's 3 factorial for the N's. So 6 factorial, which is your choices of the other 6 letters, divided by the repeats. And that's 120 ways in that or in which that can be done. There you go, 6 factorial over 3 factorial. That's 1.5. Try 1.6, ne? Try 1.6. Let's see. Try 1.6. Right, let's see how that works. So 1.6 says how many word arrangements can be made if the word ends with letter N. Okay, so N must end. So this must never change. So the other 6 can work it out whichever way. Right, the repeats are, so I've used one n, there were 3 n's. So there's 2 n's remaining. And then the other repeats are the i's that are remaining. So your answer is 180 ways. There you are, 180. All right, let me know where there's a struggle. I see different numbers in the chat, 180, banbani, and stuff like that. Just talk to me, family. Let's see how that goes in that aspect. Okay, maybe just to make it a bit more fun, let me give you a question. Yeah. Let me give you a question. Full question. Example 2. Maybe write this down. Things with repeats. Example 2, right there. Maybe someone is still writing this. Yeah. Example 2. Nazo. Let's go. I'm going to give you like 5 minutes or so. Let's go. 1 more minute. I'm ready. Here we go. Consider the word technology. How many word arrangements can be made with this word if the repeated letters are treated as identical? So I think there are 10 letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the repeated letters are treated as identical, that means here I'll have 10 options here, then 9, 8, blah, blah, blah. That's 10 factorial, which is here. So let me just write this as 10 factorial. Hold on. Which is 300. No, that's 3,628,800. Wow. If they are treated as different letters, that's what you have. Okay. 2.2, how many word arrangements can be made with the word if the repeated letters are treated as identical? This time they are treated as identical. So let's see. I have 10 options, and then I divide by the repeats. Which letters? Oh, O. All right, so there's only 2 O's, 2 factorial. So that becomes 1, 8, 1, 4, and then 400. That's what you have. That's 2.2. Then 2.3. All right, 2.3 says how many word arrangements can be made with the word if it starts and ends with the same letter. So it must start with O, end with O. Then here you have 8 letters because I've used the first O, I've used the second O. So that's 8 factorial. There are no repeats. So it's 0 factorial for the repeats. It gives you 8. 0 factorial is 1. So you may know, don't say, divided by 0. No, it's 0 factorial. Just to acknowledge that there are no repeats. So it's 8 factorial here. So your answer is not 8, your answer is 40,320. There you go. That's 2.3. Starts and ends with the same letter. Then how many word arrangements can be made with this word if the word starts with the letter O? All right, starts with the letter O. Okay, this time it starts with the letter O. So that means I have 9 factorial options. And still, there are no repeats because there's only one O. The other O will be part of the 9. It's not repeated. So it's 9 factorial over the 0 repeats, which is 362,880. All right, the last one for 2.5. How many word arrangements can be made with this word if the letter ends, if the word ends with N? Ends with N. So it ends with N. Okay. So I've got 9 factorial options here. But this time I need to consider the repeats because it ends with N. The repeats are O, the letter O. So it's 2 factorial, which is 181,440. And these are your answers for rule number 1 up to rule number 4. So basically, just to close off our session for today, The whole idea was to teach you the counting principle, the rules, and get you a basics of this. I am going to do the part with more past exam papers. These are questions that you can find in the exams as well. But I'm going to do the part with more past exam papers. You see, I had this part. I have this part, past exam papers, quite a number of them that I have, like quite a lot of them that I have prepared for you. But I only can end up to here. Then I'll do part 2 of this. But if you feel like you've understood part 1, then yeah, I think that's fine with me. But guys, the questions can be a bit tricky in the past exam papers. So we'll see how that goes. I will keep you guys updated. I will upload this on my YouTube channel as well, and be able to get you guys to watch it as many times as you want. Thank you. Thank you so much for attending today. I think you can also do what Africans do. When someone does something that's nice for you in Africa, we thank them. Sikhulise kahle thina kithi, siyabonga. Umuntu ekwenzele into ekwenzele kahle nawe uyabonga ke. So thank you everyone. Look at you. Ugogo left us with a genius. That makes me very happy. Thank you. Really appreciate that. And may God bless you all. May we continue winning. Let's not give up on anything. I'm going to stop the recording right